Good afternoon, ladies and gentlemen. I am Ne Yang from Tsinghua University. It's my pleasure to introduce our research to you. My topic is H3K27M Mutations prediction for Brainstem Gliomas based on Diffusion Radiomics learning. Brainstem gliomas are a group of highly heterogeneous tumors that occur in the brainstem. The H3 mutation, which is related with highly invasive tumor, can serve as a qualified biomarker for diagnosis, prognosis, and treatment planning for BSG. However, surgical biopsy has limited its wider clinical implementation. Accurate presurgical prediction of H3 statuses based on preoperative neuroimaging is of great clinical value. Nowadays, a few studies have been carried out to do BSG preoperative diagnosis from multi-modal brain images. For example, some models using radiomics and clinical features were developed to predict H3 mutations based on local morpho-metric features by extracting features from structural MRI. But these studies usually ignore glioma's influence on the brain connectomics. There are also some models for BSG preoperative diagnosis based on the global connectomics features extracted from the brain networks. However, the problem lies in ignoring the highly heterogeneous tumor characteristics. How to effectively fuse these two kinds of multimodal information still remains a challenge. Recently, graph neural networks have been proposed to tackle this issue. Many GNN-based methods for solving neuroscience problems were carried out based on various graph-related tasks, such as graph classification. For example, the work by Huang proposed a diffusion-convolution GNN to integrate functional and structural connectivities from multimodal brain image. Notably, the brain graph is a natural fit for GNN models. Therefore, based on graph structure, we can integrate multimodal information seamlessly. And also, the cross-modality brain representation can be automatically learned through the supervised graph classification. In order to give the prediction of H3 mutation from the perspective of brain networks, we proposed a novel radiomics analysis model for multimodal information fusion using deep graph learning. First, the SMRI-based radiomics features are extracted from tumors, and the DMRI-based tractography are parcellated biomerged antennas. Then, the multimodal information is coupled to construct brain networks. Specifically, the node features of brainstem are governed by BSG radiomics features. Finally, the graphs are fed into our proposed multi-mechanism diffusion-convolution network to encode diffusion radiomics, which performs H3 mutation prediction and derives a brain saliency map associated with gene expression. A brain structural network can describe the interaction between paired brain regions using a graph structure G. In order to couple local radiomics with global connectomics seamlessly, we adopt the Diffusion-Convolution Kernel to design the diffusion process of tumor radiomics information along brain network. The potential expression of brain network X diffusion can be learned via graph diffusion for BSG preoperative diagnosis. In order to obtain a compact and discriminative representation, we proposed a multi-mechanism diffusion-convolution neural network, and the graph-structured brain networks based on tumor radiomics and structural connectivity matrix are fed into our network for learning diffusion radiomics. The network can be divided into three parts for node embedding, node pooling, and graph classification, respectively. First, redefine the transmission matrix P in the traditional graph diffusion convolution kernel to improve the graph representation learning. We integrate multiple metrics of structural connectivity to define a MMDC kernel, which can increase the learning ability of the model. Then, we adopt the idea of graph attention networks to learn dynamic edge weights for the dynamic adjustment of the transmission matrix. Finally, the transmission matrix PMMDC and the whole diffusion convolution on the feature matrix X can be like this to generate node representations. Then, to generate smaller graph representations and thus avoid overfitting, pooling and readout operations were carried out. The graph pooling layer coarses each graph into a subgraph in a self-attention manner based on both the node features and graph topology, and thus perform node selection for H3 mutation prediction. The readout layer translates node representations of each graph into a graph representation. Finally, by applying a multi-layer perception to graph representations, we can perform graph classification. Our proposed method is verified on a real BSG dataset. We also compared it with 5 competing methods for H3 genotype prediction. According to the input of the model, these methods can be divided into 3 types. As shown in the result table, our Diffusion Radiomics model achieves the best performance for H3 mutation prediction task. When using radiomics and connectomics features separately, radiomics-based methods achieve higher accuracy, while connectomics show higher specificity. Multi-modal-based methods can help improve the prediction performance, indicating the benefits of integrating local radiomics and large-scale connectomics. Moreover, the diffusion radiomics generated by our model could improve the discriminative power of the original features by achieving a deep fusion of cross-modality information. Then, to explore influence of each component in our model, 5 variant models were evaluated as an ablation study. As can be seen, integrating multiple structural connectivity metrics can help improve the prediction performance. Removing the attention mechanism and pooling layer could cause a significant decrease in performance. Then, to evaluate the contributions of our proposed MMDC kernel, an analysis of the diffusion map on the group level is carried out. The group differences of the original diffusion maps were calculated on the 3 types of structural connectivity. We can draw some interesting observations. First, compared with the original predefined diffusion, there are more discriminative connections. Second, while attention diffusion, discriminative connections of diffusion maps concentrate in several specific brain regions. In addition, we investigated the most important brain regions affecting the H3 prediction. By averaging the node importance scores among all the subjects, the group-wise significant ROIs associated with BSG diffusion radiomics spread at the whole brain. Specifically, the involved cortical areas play vital roles in motor, sense, and emotion controls. The findings of this study may help to further explain the mechanism of emotional personality changes in BSG patients. In conclusion, we proposed a novel BSG preoperative diagnosis framework based on a deep graph learning, which achieves a deep fusion of local radiomics and global connectomics via diffusion radiomics. Our model not only performs better than alternative methods on H3 mutation prediction, but also gives interpretable results, revealing the significant brain regions related to gene expression. In the future, we will validate our methods on larger benchmark datasets, and we also plan to extend our model to a spatial temporal model and apply to characterize the neurodegeneration in Alzheimer's disease. That's all for my presentation. Thank you for your listening, and welcome for any question.